Okay, well, thanks everyone for coming again. This is to the Foundation of Probability seminar. Happy to have Yonatan Berman talk from London Mathematical Laboratory in CUNY. He'll be talking about work on risk preferences in time lotteries. Okay, take it away.
Thanks, Harry, for the invitation. And it was actually, as some of you may know, this seminar was supposed to happen in late March, I think. And it didn't. And so I'm really happy for the invitation, and that's great that we can still have it virtually, remotely. So what I'm going to talk about today is something quite simple that is called time lotteries, which is a type of lottery that I will soon introduce. And the idea of this paper that I'm going to present, this is the first part of my talk, is just to try and analyze or to give a theoretical framework for how we can think about decision-making in time lotteries and how it fits the, let's say, the standard theoretical framework in which traditionally people can think about time lotteries, and how it fits experiments that were done. And then what I'll try to do in the second part of my talk, which some of you may be familiar already with things that I'm about to show, is basically how this fits in the agenda of what we call ergodicity economics. So how time lotteries is essentially an example of the way we think about decision making in general in economics, but how it differs from many other problems or many simple problems or simpler problems that so far we've studied in ergodicity economics, and why this one is actually quite interesting with respect to others. So let's just start with what is a time lottery. So a time lottery is a super simple a super simple type of lottery. It's essentially a known payment, so some delta X measured in, say, in dollars, and two possible payment times. So we have T1, that's an earlier payment time, and T2, a later payment time. And then we have a probability P to receive delta X at the earlier payment time, meaning probability 1 minus P, and actually it doesn't mean that, but we have probability of 1 minus P to receive the payment at T2. That's a time lottery. Known payment that is not random in any way, just a payment amount, two possible payment times, and a probability to receive the payment at the earlier payment. Okay? That's a time lottery. Every time lottery defines a unique timed payment, and the idea of the timed payment that corresponds to a time lottery is that this is the same payment amount that is received in a known time, or in a certain time. This is why we call it a timed payment, and this time is the expected payment time of the time lottery. Okay, so if it's a very simple setting that, I mean, is really central. So if someone has a pressing question about it, now it would be a good time. It's just, really simple. Payment amount delta X, two possible payment times, probability to receive the payment at the earlier payment time, and this defines a timed payment, which is just the same payment amount at a payment time somewhere in between T1 and T2. Okay. And the basic question, the decision question that we are facing or that we're interested in is how would decision makers choose between the timed payment, between the time lottery and the corresponding time payment. The standard EDU, expected discounted utility, or if you'd like, the standard decision theory in microeconomics, I would say, would basically treat this problem is in a rather simple way, which I'm not going to show you, but it's very easy to take expected discounted utility, pick a utility function, pick a discounting function, and use expected utility theory to reach a very simple conclusion, which is that decision makers should be risk-seeking. They should choose the time lottery over the corresponding timed payment. However, experimental observation, so in experiments that were done in the last, say, over the last 20 years or so, but more so because perhaps I think you'll all find this problem very simple, but perhaps surprisingly, it wasn't really studied so much. So, I mean, the main paper about it in the economics literature is actually just, it was published during the last year. So this is not something that is well studied. I'll touch that in a second. But basic thing I want to say about the experimental observation is that we don't find decision makers to be generally risk-seeking, but also not necessarily risk-averse. So it's not clear whether decision makers are categorically risk-seeking, so preferring the time lottery and not necessarily risk-averse. And when I say risk-averse in the context of time lotteries, I mean would prefer the timed payment, which is riskless.
Could I stop you for a minute just to try to understand better?
Sure.
Why is the standard prediction? I didn't understand that, the standard prediction. Maybe I didn't. Maybe I missed something on the previous slide.
No, it's not that I didn't prove it, but any convex discount function that you'll choose and any utility function that you'll choose would give you a result that says that decision makers should prefer the time lottery over the corresponding time payment. I mean, I didn't prove it. I can prove it. The proof is essentially Jensen's inequality. It's nothing more than Jensen's inequality, but it's quite easy to show that. So this is what I mean by the standard EDU prediction.
So it relies on the idea that the assumption that you're discounting.
Sure. Yeah. I mean, it's EDU here. I mean, expected discounted utility. That the model for making a decision is taking the utility you get from the payment, discount it to the present, and then take the expected or the expected value of this.
And when you say the experimental observation, does that mean people behave differently? They don't all.
It means that in experiments, I'll touch the experiments later on because they are not very, very good, but most of them are not very good. But generally speaking about the experimental observations that we have on that, you can't reach a clear-cut conclusion as to whether people are risk-seeking or risk-averse. And okay, so the paper I'm presenting right now is essentially, can we reconcile theory and data by assuming the decision makers are growth optimal? So I'll explain what I mean by growth optimality very soon. But the idea is that that the criterion for people to make choices is based on what happens to their wealth over time and not to their utility in expectation. So just a few words on the literature. So as I said, there is not a lot. There's not a lot of literature on this problem, and the main paper was published in Econometrica less than a year ago. They make some experiments themselves, but it's basically a theory paper trying to reconcile those. I mean, this is also this paper that time lotteries and stochastic impatience is in a way another theoretical approach to reconciling data and theory. There are a few experimental or empirical papers from earlier in the 2000s, but that's basically it. However, in behavioral ecology, it's quite interesting that a very similar problem was studied in the context of mainly of foraging theory. So in the 80s and the 90s, there are a few papers on that, experimental and theoretical. And interestingly, animals are risk-seeking almost always in all experiments on time lotteries in animals. They are found to be risk-seeking, like people are predicted to be, at least by standard expected utility theory, discounted utility theory, but people are not, apparently.
Is
And
this, go ahead.
And as I mentioned in the beginning, I'm going to say a few words on how this is related to a larger literature that this paper is basically a part of, which is about growth optimal behavior in humans, both experimentally and theoretically.
I just had a question. If this, I've seen some literature before on sooner, smaller rewards versus larger, later rewards. I don't know if this means anything to you, but psychology experiments where they offer somebody a smaller amount now or a larger amount later, whether they'll take it. Is that, I know that's different from your setup, but does that fit into any of what you're talking, this literature that you've referenced? Or?
Maybe I should have mentioned that, because discounting is a huge thing in economics. So how you make choice, how you choose between two different payments at two different times. This is quite a basic problem, and which I'm not going to talk about explicitly here, simply because it's quite interesting how you make one small change, which is to make the payment the same at two different times. That makes a huge difference, because if we had this extra degree of freedom of having a different payment amount, it would not only make things more complicated to calculate and everything. It's just conceptually different. But basically, at least from the way you phrase it, this is what economists would simply call discounting. So temporal discounting. And there are ways to, the standard way is, okay, you have a payment, a later payment with a higher amount and a smaller payment with a earlier payment time. So you have a way to discount the payment so that now you could make a choice between the two. So of course it has some similarity to this problem, but it's different.
I'm still a little confused too. I'm sorry, but who assumes that people are risk-seeking? That you're talking about the utility curve being convex instead of concave?
The discount function. So the discount function is the assumption is that it's convex. The utility actually the utility doesn't matter. The utility can be whatever utility you want. So for any convex discount function and
I see. Discount function is convex. Okay, thank you.
And any utility function. Okay, so what do I mean by growth optimal behavior? So the postulate basically of this paper is that we're going to evaluate time lotteries under the assumption that decision makers maximize the growth rate of their wealth. And a growth rate is something that is defined based on the wealth dynamics. And the wealth dynamics can take different forms, and the different forms of the different dynamics would correspond to different forms of growth rates. And I'm not going to talk about it too much now. I might talk about it a little bit later, but now we'll just assume, and it also fits the setting that I presented in the beginning, that we look at additive dynamics. And what I mean by additive dynamics is that we can look at the wealth at a given point in time as a wealth in some earlier point in time plus some rate times the multiplied by the time difference. And this rate is, for additive dynamics, this is the proper growth rate. Okay, the proper definition of a growth rate in additive dynamics would be to subtract the earlier wealth from the current wealth and divide by the time interval, and this would be the rate of growth of your wealth under this dynamic. For example, if we had exponential dynamic or multiplicative dynamic, then this wouldn't work, right? So I'm not going to talk too much about that. It's just a simple way to define a growth rate in our setting. So let me define what we mean by growth optimal over time lotteries. This is, I suppose that not for all of you this notation is familiar, but this is just an economic theory way of defining preferences. Okay, so we define a preference relation over time lotteries, and this preference relation would be considered time optimal if for two time lotteries, LA and LB, with growth rates GA and GB, we will always choose the one that corresponds to a higher growth rate, and we will be indifferent between the two time lotteries if they correspond to the same growth rate. I still didn't tell you how I define a growth rate for a time lottery. This is something I'll do soon. But suppose we had two time lotteries and we had the growth rate that corresponded to each, then our choice would be growth optimal if we would always choose the time lottery that corresponds to a higher growth rate. This sounds, I mean, it may sound trivial, it may sound stupid, but it's just a definition. And apparently, and again, this is not something I'm going to prove now. The proof is really not interesting for in and of itself, but these kind of definitions are what we could call rational. So this is rational choice. It satisfies the basic axioms of rationality. So, you know, such as transitivity and independence and the von Neumann-Morgenstern axiom. So the basic axioms of rational choice, if you'd like. So these are growth optimal behavior. And now the question is, how can we, based on the definition of the time lottery that I gave you in the beginning, how can we now move from this definition to
So the time lotteries are always just two, this thing where you have two different points in time, it's not 3 or 4, it's always 2.
Yeah. So a time lottery is just, you know, a payment amount, 2 payment times, 1 probability. So, okay,
Sorry,
we have a time payment. So,
sorry, just to be clear, the definition of growth rate also doesn't take into account the probability, right? So 2 time lotteries that have different probability but take place over the same interval of time and have the same delta x, the payment would have the same preference ordering.
so this is this slide. I hope this slide will answer this. So for a timed payment, suppose we didn't have any probability, you know. So a timed payment, meaning a payment amount delta x and a payment time t, this would correspond trivially to this growth rate. So just the payment amount over the time interval that elapses until the payment. So just delta x over t. In a time lottery, we have basically 2 possible timed payments with different probabilities, right? So we have 2 growth rates in a time lottery. We have the growth rate that corresponds to the LDL payment time, GM1, which is delta x over T1. And we have a later payment time, and we have another growth rate that corresponds to the later payment time, which is GM2, which is simply delta x over T2. So we can think of this growth rate of a time lottery as a random variable. Okay? It's not a scalar, it's a random variable. So this, the way I wrote it, is not very useful, right? I mean, the way I presented growth optimal behavior, I needed a scalar. I needed to compare 2 scalars when I was comparing 2 time lotteries. So we need to find a way to collapse this random growth rate into a scalar. So we have 2 ways to do it, or we are going to talk about 2 ways in which this can be done. And the first way, which is, as I'll try to show you later, it's basically the ergodicity economics way, is basically to say that the scalar growth rate that corresponds to the time lottery is the long time limit of the random growth rate. Okay, what does it mean? So it basically the time average of the random growth rate. And what does it mean? It corresponds to the growth rate that is experienced by the decision maker if the time lottery is just drawn indefinitely time after time after time. So suppose we just repeat the time lottery. Let's say once it was T1, then it was again T1, afterwards it was T2, then indefinitely. Okay? So if we look at this indefinitely, we can think about, you know, wealth will change over time, yeah, at different points in time. And we can think about what would be the growth rate in this case. What is it? So it's just the limit for t goes to infinity of the total payment after t rounds. Okay, let's say we are playing t rounds and then we take t to infinity, divided by the total time that elapses after t rounds. So after t rounds, we have obviously t times delta x, divided by n1 times in which the payment was received after t1, after time t1, plus n2 times in which the payment was received at the later payment time t2. And it's easy to see that when we take t to infinity, the number of rounds to infinity, then n1 over t is just the probability to get the early payment time, and n2 over t is the probability to get the later payment time. So it's just p plus pt1 plus 1 minus pt2. So what we get here is this very simple result, that the growth rate in this limit is simply the payment amount delta x divided by the expected payment time. So PT1 plus 1 minus PT2. Okay, so this is the scalar growth rate in this approach. Another approach is the ensemble approach. In this case, we think about the scalar growth rate as the expected value of the random growth rate. So we saw that the growth rate in a time lottery was a random variable. So a simple, perhaps the simplest thing we can do if we want to make a scalar out of a random variable would be to take its expected value. This corresponds to essentially a case in which the lottery is simultaneously realized n times, and then just taking the average of these n realizations and then take n to infinity, right? So we can think about it as just the limit of n goes to infinity of 1 over n plus basically the arithmetic mean of n realizations of the random growth rate. And as you can see, this result yields something that is different. It basically yields, as I said, the expected value of the random growth rate, which is slightly different with what we saw before. It's p times gm1 or delta x over t1 plus 1 minus p dx over t2. So we have two approaches, and interestingly, they give us two predictions. How can we show that? So if you remember, the basic question that we wanted to ask was, how would decision makers make a choice between a time lottery L and the corresponding timed payment? So first, the timed payment is easy to know what the corresponding growth rate, right? It's just delta x divided by the expected payment time, right? This is the payment time of the time payment that corresponds to time lottery. The time approach predicts indifference between the time lottery and the timed payment, right? Because if you recall just the previous, not the previous slide, but the one before that, we saw that the time approach, or the time average growth rate of the time lottery, is the same as the growth rate of the time payment. It's simply delta x over the expected payment time. However, we saw that the ensemble approach predicts that decision makers are risk-seeking, because this growth rate, which the growth rate of the ensemble approach, is the expectation of delta x over t, which again by Jensen's inequality is larger than delta x over the expected payment time, which is again the growth rate of the timed payment. So just a quick recap of this slide is that we had a random growth rate in a time lottery, and the question was whether a time lottery is preferred to the corresponding timed payment. We had two ways to make the random growth rate of the time lottery a scalar. One of these approaches predicts indifference between the time lottery and the timed payment, and the other predicts risk-seeking behavior. Both of these approaches are still growth optimal in the sense that I defined before, okay? Remember that here we are making the assumption that a decision maker should choose the time lottery that corresponds to a higher growth rate. And this is the reason the time approach predicts indifference and the ensemble approach predicts risk-seeking behavior. So I hope that's clear so far, and it's important to say a word about the ensemble approach. The ensemble approach is equivalent to discounted expected utility for hyperbolic discount function and linear utility. Okay? I mean, it would look exactly the same, but the calculation itself wouldn't be very different if we choose just a general utility function and a general convex discount function. Okay, but it's not very important. What's important is just this idea that we have two approaches to calculate a growth rate or to define a growth rate for a time lottery with two different predictions. So we would like to put the predictions to test using some experimental data from previous papers. So now it's basically a contest between those two approaches, between those two predictions, who's right and who's wrong. So basically what we are going to do is to take each experiment that was done in these papers. In each case, in each experiment, we are going to calculate by the parameters of the experiment the growth rate in the ensemble and the time approaches. And we're going to look at the experimental results, which are given as the fraction of subjects in the experiment who chose the less risky options. In other words, they were risk averse. So we are looking at how many risk averse, or what is the fraction of risk averse subjects in each experiment, and how this depends on the different growth rates. So this is how it looks like. So the y-axis of this graph that you're seeing is again the fraction of subjects who were risk averse. The x-axis is the difference between the ensemble approach growth rate and the time approach growth rate. So as we go to the right, it means that the time approach growth rate, as we go to the right on the x-axis, it means that the ensemble approach the ensemble approach growth rate becomes larger compared to the time approach growth rate. 0 means that they are equal, and equal means it's not a time lottery. Okay, equality, it's something that I didn't say before, but equality between the time approach and the ensemble approach only occurs if the probability is 0 or 1, or that the payment times are equal. Okay, this is the only case in which we have the same growth rates, which basically means the time lottery is not really a time lottery. So if it is a time lottery, we'll always have the ensemble approach growth rate larger than the time approach growth rate. So the x-axis here again is the difference between them. The y-axis is how many subjects, or what's the fraction of subjects who were risk averse. So they chose the timed payment over the time lottery. Each circle is one experiment, basically. Okay, so in this paper that we are looking at now, this is the better experiment of the two that I'm talking about. They made 10 different experiments, and each experiment corresponded to different parameters. So each circle is one experiment. And what we basically see is something very clear. First, it's clear that there is no clear-cut answer to whether people are risk-seeking, risk-neutral, or risk-averse. Because if they were risk-seeking, all the experiments would have been around 0 here, regardless of the x-axis, right? This basically means risk-seeking behavior. It means that all the subjects are not risk-averse. Being risk-averse, or if people were risk-averse, then it would always be around 100%. Risk neutrality is not really something that such an experiment can test. It's just, I mean, risk neutrality it's not really a prediction on the fraction of risk-averse subjects. You could say that risk neutrality means that half of the people will be risk-averse, half of the people would be risk-seeking, but not really. It's just not a prediction on the result. Okay. But what we see here is that definitely no clear-cut answer as to whether people are risk-seeking, risk-neutral, or risk-averse. But there is still a regularity, and this regularity is quite clear. That as the ensemble average gets larger in comparison to the time average, decision makers are more likely to prefer less risky lotteries. Okay, so even if we thought that, you know, the prediction of 100% risk seeking, so 0 here, okay, this is, I mean, we couldn't have believed that this would actually be the result. At least we would have liked this trend to be downward sloping rather than upward sloping, because as the ensemble growth rate becomes larger compared to the time average growth rate, we would expect at least that the risky, the time lottery is more attractive than the timed payment, right? So the more right we go on the x-axis, basically means that the growth rate of the time lottery is more attractive than the timed payment. This is clearly not the case. The regularity is actually on the opposite direction, meaning that the more attractive the ensemble approach growth rate looks like, the less likely people are going to pick the risky time lottery. Okay, so this is definitely a falsification of the ensemble approach. However, there is no verification or falsification of the time approach. As I said, we can't really use this experiment to say much about risk neutrality prediction, just because risk neutrality doesn't predict a specific number or fraction of risk-averse subjects.
So I just had a question here, since so this graphic is using an ensemble type of statistic, right? In that you're counting the fraction of individuals who fit in each category in
Yes.
each of these different experiments. I'd be curious, maybe you would be too, that, well, I assume you don't have this type of information, but if you were to put the same person into these different experiments, whether they would behave in a consistent manner somehow.
Yeah, this is actually very sad, because these experiments were done on a group, the same group of people. I think so. These 10 experiments were done. Basically, we see here 2 groups of people. So it means that potentially they could have asked the same people. They could have shown the results actually by subject, and not the way that I mean, not the way it's described, meaning not just as a fraction of the entire ensemble. And you're definitely right. Yes, this is an ensemble statistic here that we're looking at. Unfortunately, we can't say much about a specific person, whether, yeah, unfortunately I can't, but yes.
But that's how it was reported. I'm just
Yeah, this is
yeah.
the experimental design. I mean, if I would have designed those experiments, I would do things differently, but sure. It's still a pretty solid experiment, in the sense that they put a lot of effort to do it well. You know, it was incentivized. You know, people could not, I mean, they planned it relatively well, I would say.
So this choice is between the lottery and a midpoint, right? And that midpoint was defined which way?
It's defined basically as just the weighted the weighted, it's the expected value of the payment time, if you'd like. So the midpoint can be very close to the earlier payment time if P is close to 1, and when P is close to 0, it's very close to T2. It could be anywhere.
So, I see.
But I think that in those experiments,
It's not the way the expected, okay. So it's sort of, the midpoint is that this alternative is defined according to your theory, not according to expected utility theory.
why do you say so? No, I mean, the midpoint is just, it's, in this case, the way
It's the time,
I define the, actually it's not I define, but because it's also in paper before my paper, the way that you think about a corresponding timed payment to a time lottery. And then you ask the question of which is preferred.
So Harry's question is sort of getting at whether you would expect people to be doing similar on how they behave.
Yeah, I mean, you can ask different questions on, if you would ask how people change their minds, for example, a specific person would change their mind if you change some parameter. That might have been more, a better way to test these predictions rather than look at the ensemble. But for sure, if we'd, I mean,
correct. Am I correct to guess that these are college students, sort of middle class college students?
Yeah, college students in Wharton.
Yeah.
And the typical payment times were on the order of magnitude of the weeks. Weeks. So they were taken to the lab, and in the end, the choices they had to make was something like, do you prefer, no, it was something like $15 in 3 weeks. This is the, this is typical.
So kind of inconsequential for these people.
Maybe, so few weeks, not many weeks, and I think 10, 20, 30 even dollars.
Yeah, but they weren't, I mean, the choice was not a consequential choice for them.
They actually, the idea that after, so the way these experiments were designed was that in the end of the experiment, of the end of the session, one of those experiments was actually realized. They didn't, I mean, it was a randomly chosen experiment of all questions they had to answer was realized, and then they could go, say, 3 weeks later to pick up the money.
No, what I mean is not that it didn't have consequences, but that these people didn't really care very much.
Oh, yeah, in that sense. Well, it's not a, yeah, I mean, it's hard to say whether this is, if they cared at all about this sum of money or not. Yeah. I mean, it's still better than the other experiment, than this experiment, for example, which was essentially non-consequential in the sense that no lottery has been realized. It was just, you were paid a few dollars to participate, and then you had to make choices. So this is another experiment of the same type, which much less can be said about, and but still, I mean, the qualitative results, the qualitative message, I think, is the same in the sense that it definitely shows that the ensemble approach is not a good thing in predicting how people behave. People are definitely not risk-seeking. Yet we don't see something here that falsifies the time approach. So basically these are the conclusions of this paper. are basically these, that growth optimal behavior predicts either risk-seeking or risk-neutral behavior, depending on how we associate a growth rate with the time lottery. We have two approaches, the ensemble approaches and the time approach. The ensemble approach uses the expected value averaging over an ensemble. This growth rate is not physically achievable in the sense that we can design a setting in which this growth rate will be actually felt by the decision maker. The time approach uses the long time limit, which is physically achievable because we can always just repeat the time after time after time after time. But at the same time, this concept, this limit may not be compatible with the decision maker choices if the time horizon is realistically short. So it's not clear a priori which one is actually preferred by decision makers. And it seems like the time approach is slightly better aligned with the experimental evidence simply because, I mean, first I need to say that the experiments are not distinguishing in this case, but they are better aligned in the sense that it does predict this risk neutrality or indifference, which I would say translate to a certain degree to some spread over the y-axis. And it's possible that what we see here, this trend, is basically when the prediction is indifference, when the prediction is risk neutrality. I mean, there might be some second order effect that that create this regularity that we are just not modeling. This is possible. I don't know, but the important thing here is that it definitely doesn't falsify the time approach. So, okay, I won't have time to go. Okay, I hope most of you seen this already, but what I want to touch is just a very interesting thing, I think, about what
I'm sorry.
Yeah,
could I ask you one more time about what you just went through?
Yeah.
When the ensemble G bar gets bigger, what does that look like in terms of where those points are on the time axis?
Okay, so when the ensemble,
or in terms of the probability, what does it mean in terms of that probability P? Are you looking at a probability that is closer to the lower time or closer to the higher time? How does that relate to whether the G bar is bigger, whether the gap is bigger?
So,
maybe you said that, but I was just trying to think. Remember.
No, I mean basically when the variance of the payment time is bigger. So the bigger the variance is so think about the payment.
P is 1/2 would be the biggest variance, no?
I think so, yeah.
So it was when you were in P 1/2 was when they were most likely to.
So when P is 1/2, this is when the variance of the payment time is the largest. And this is the case for which, for the same payment times, you would receive the largest difference between the ensemble growth rate and the time approach growth rate.
And so this is where people are what you call, this is where you say people are more risk seeking in this context.
No, I mean, this would look like, for example, in this graph, it would simply correspond to be very high on the x-axis. So, I mean, it seems like, so suppose, okay, this is, this is just a trend line, but think about, the point here, I don't know if you see the cursor, around
yes.
$8 per week. So the experimental results basically tell us that the bigger the difference is, the bigger this difference is, the more likely that people will be risk averse, meaning that they will prefer the less risky or the not risky at all lottery rather than the risky lottery.
Well, I guess I'm still confused. When P is 1/2, where is that on the graph?
Each point, so the parameters are quite different in each of these experiments because they created, they asked 10 different questions.
Oh, I see.
The payment amounts were slightly different and the payment times and the P's were quite different. But in general, you're right that we could have, they didn't do it, but it's actually quite an interesting experiment to make. Fix delta X, fix the payment amount, fix the payment time, and go from P equals 0 to P equals 1. Or actually from P equals 0 to P equals half. This probably would be enough. But for P equals 0, you will be here at 0 difference between the ensemble growth rate and the time growth rate. And when you would increase, as you would increase P, you would make the difference between those growth rates larger and larger. And
positive difference.
Sorry?
Positive difference.
Yeah, positive difference.
So P, a bigger P means a...
right on the x-axis. So bigger P means bigger difference between the ensemble and...
It also means a bigger P means closer to it means the earlier time is more likely.
Yes. Yes. But yeah.
Okay, thank you.
Okay, so
no need to rush through anything. I don't know how many more slides you have left, obviously, but no need to rush, I would say.
okay.
There's questions.
So
yeah.
I'll try to. So the idea, what I wanted to go through now is to quickly say something quite general about ergodicity economics and to show how the problem of time lotteries fits in this approach or this agenda. And the way to show that is just go through this game that I hope at least that some of you may have seen before. So we're looking at a very simple game in which we toss a coin every minute. It's a fair coin. So it's a fair coin in the sense that each side has a probability of 1/2. But if it's heads, you win 50% of your current money. And if it's tails, you lose 40%. So it's an asymmetric fair coin. And the payout is fractional of your wealth. And suppose we toss it every minute. Okay, so suppose you start with $100, then after 5 minutes you'll have few heads, few tails, etc. Your money changes multiplicatively over time. And then the question is, who wants to play? I'm not going to ask you this question, but I suppose that some of you would like to play and some of you won't. And at least rhetorically, I will assume that. Maybe none of you would like to play. And how can we, again, it's a decision problem, right? So the question is, how can we make up our minds on whether it makes sense to play or not? So one way to think about it would be to start playing. And now suppose we play for 1 hour, so 60 minutes, 60 tosses. How would your money look like? Well, we just move randomly, and it's quite hard to say much about this random path. So we can look at 10 sequences of the same 60 coin tosses, and many of them go down, some of them go up. It's not clear whether it's a good game to play or not. We look at 20, it's all over the place. So a natural thing to do would be to average over them. If we average over 20 sequences, we don't see much. If we average over 1,000, well, this looks a bit like something that increasing. And we have 1 million sequences of 60 minutes, then basically we see clearly that we have an exponentially increasing path. So at least when we think about it this way, the game is worth playing on average. But not everyone wanted to play. Probably most of you, I guess, even didn't want to play. And the question is why? So expected utility theory would introduce utility. It would say that the optimum that people optimize is not the expected change in their money, because people perceive the usefulness of money in a subjective way and concavely. So we introduce a utility function, and then the optimum is just the expected change in utility. And the interesting thing to note here is that we have the expectation, the expected value, and we have subjectivity. Okay, I'll skip. Actually, I won't skip that. Just to show that if your utility is linear, then it makes sense for you to play in EUT, and if it's logarithmic, then you won't play. Okay. And indeed, if we look at 1 million sequences of 60 minutes, we see that money grows exponentially, but utility actually decreases over time. So if your utility is logarithmic. So expected logarithmic utility would result in something that decreases over time. So it doesn't make sense to play. And then there's the ergodicity question, which is the expectation value also the average over time? So we can play for a long time and see what happens, right? So we play for 60 minutes, and this is how it looked like. We can continue playing, say, for 24 hours, so 24 times 60, and you see here in black the first 1 hour, which looks nothing in particular, and in gray here you see how the previous average sequence looked like. So sorry, this is this. Okay, so now if we play for 24 hours, now it looks like the money decays over time, and it continues to decay if we play longer. And obviously, if we play long enough, this really looks like an exponential decay. So we had two perspectives. We had the Ensemble perspective, in which we looked at 60 minutes, many observations, and we averaged wealth, and it looked like the growth rate is positive. And we had the time perspective, in which we play one sequence, but just very, very long one, and then it looks like the growth rate is negative. And when they're not equal, this is what we would call a non-ergodic. I mean, in this particular case, we would say that wealth is a non-ergodic observable. So an interesting thing about what we have here, we know that maximizing expected change in wealth is not a successful model. So EUT, as we said, keeps the expectation value, but it replaces money with the utility of money. And ergodicity economics, which is similar to what we did in the time lotteries, if you remember, the idea is to keep money, so not go through utility basically, and replace the expectation value with a time average growth. And the question is whether these two approaches actually meet something. The answer is yes. And it's quite interesting because, at least mathematically speaking, this would look quite similar. In what way? So we start from some lottery, if you'd like, or some initial conditions, so initial wealth and some change in wealth, or some lottery. In EUT, we know we have a utility function. We look at the expected change in utility. And if we want to say something about how this grows over time, which is not usually done in EUT, but still we can do it, we can simply ask this question: what is the growth rate of the expected change in utility? Okay, that would be a growth rate that is defined based on this optimand of the expected change in utility. In EE, the idea is to look at the dynamic of wealth, so how wealth changes over time, try to find a linearization of this dynamic, and then take this growth rate, so delta V, so the linearized wealth over delta T, and then take delta T to infinity, which, if you recall the time lotteries, yeah, the linearization wasn't needed because it was already linear. So we just took the delta V was delta X after long enough time, divided by the time interval that, again, we took it to infinity. And then the question that we ask is whether these growth rates are the same. So in many cases, this is indeed the case. We can find, I mean, it's possible to find a utility function and a linearization such that these two growth rates would be the same. And this is definitely possible. They would make, EE and EUT would make an identical predictions if the utility changes are ergodic. In the coin toss example, this would be the case if the utility is logarithmic. If the utility is logarithmic, then the behavior prediction of the two approaches is identical. And we can do the same for any dynamic, if you'd like, in any utility function. A utility which is linear would correspond, if you'd like, to a dynamic that is defined by this stochastic differential equation. Basically, this is just, if you'd like, a random walk. Logarithmic utility would correspond to a slightly more complicated, basically geometric Brownian motion. Right? But it's possible to take other utility functions such as square root of x. And we can also find a transformation and can also define a stochastic process that corresponds, that this stochastic process, if we look at wealth under this stochastic process, in EE, that would make the same behavior predictions as EUT. And the reason I'm actually making this point is because in time lotteries, this is not the case. So are EUT and EE are equivalent? The answer is definitely no. In time lotteries, this trick doesn't work. And it doesn't work because we cannot find a transformation such that the ensemble average and the time average growth rate are equal. So if we go back to this diagram, we will not be able to find U and E, or for a given U, on the dynamic, we will not be able to find the V so that we'll have here equality. And we still saw that we got different predictions. So this is quite an interesting thing because it's the first example of the first problem that we have looked at in which we can't make the growth rate ergodic. We can't look at a transformation of wealth over time so that the resulting growth rate will become an ergodic observable. So just to conclude, of the bottom line of the talk is that EE seems to be slightly better aligned with experimental evidence than EUT, but we still need to design experiments that can verify the time approach properly, which I hope is true. Maybe it's also has nothing to do with how people make choices in time lotteries, but still I'm quite hopeful that it is going to give better predictions than EET. Thank you.
Hey, thanks for that.